So I'm going to be live streaming this, so I am going to be sitting here while this is going on. Just be aware of that. I'm not going to be getting up and dancing around like an idiot like I usually am. So, because I have to make sure I'm close to my microphone so the people who are here with us on the live stream can hear what I am saying. And I don't know how many others are going to join us, but there are a couple of people. So I have to start the recording and figure out how.
Can they see us?
They can't see you, no. They can only see me.
Can they hear us?
Maybe if you were loud enough, but... Oh, God, this is awesome. Okay. I'm going to have to stop the sharing so I can start the recording. And for some reason, even though I turned the audio off, we can still hear it, which is not ideal. I know there's the record button. All right. Let's try this again. Okay, so we should be recording now. What I want to talk about today is we've kind of gone through most of the basics of the language. So we've covered syntax, we've covered data types, we've covered ways that you can branch, like if-else, we've talked about loops. We have basically covered most of the fundamental constructs of any programming language, although we've been going through Java. So today what we're going to do is we're going to start looking at how we can actually organize that data and the data that we're using within programs in more effective ways. I have a quote up here from Linus Torvalds that I really like. It's bad programmers worry about code, and good programmers worry about data structures and their relationships. Because when it comes down to it, everything we do in computing is really about the information. We're trying to share information, we're trying to manipulate information, we're trying to make it accessible and usable and meaningful. And apparently hey everybody, if you're on the live stream, if you wouldn't mind muting yourself, because I tried muting my computer and apparently that doesn't work. I'm not sure why. Oh, there we go. Okay, I think I have it. So the relationship of data to other data is really important in what we do. So today we're going to look at some ways that we can actually organize data, and some of this will be a little bit of review because we've seen some of these concepts in the past. But that's kind of the focus today. And moving forward, we're going to be talking a lot more about how we structure things and how we arrange and organize things, more so than how we do fundamental, operations within a computer, because we've covered most of that ground at this point. So a lot more problem solving and conceptual stuff, and a lot less syntax. So the first thing I want to talk about is something called abstract data types. You've seen abstract data types before because I started talking about them a little bit previously, specifically lists and maps. The idea of an abstract data type is that we have some set of behaviors that we might expect of certain classes of information. We've seen containers. We have certain expectations broadly of what containers, also known as collections, will do. Right? They hold elements of some kind. There are other types of abstract data types as well. We've talked about lists a little bit, but each one of these abstract data types has a couple of key features. For lists, we know all lists are countable. They have a certain number of elements, and we can count the number of elements in them. We know that they can have repeated values. And we also know that lists have no keys. They have only values. What that means is that we have nothing that we can look up a value with. It's just the value is there or it's not there. And they have some kind of ordering, right? So if we have a list and we put things in a list, we can change the order of that list, and that list's ordering is meaningful. So we can arrange it in such a way that we can access it consistently in the same way. Does that make sense? So that's kind of the definition of what we mean. This is the kind of the nitty-gritty of what we mean when we're talking about a list type. To give you some examples of how these are implemented, the two big ones in most programming languages, and this is true of Java as well, are linked lists and array lists. So a linked list is is a sequence of elements of memory with pointers to the next element of memory, and we're going to get into the details of that eventually. And an array list is basically an array with wrappers around it that let us access the data in a more abstracted way. We don't have to worry about the length of the array underneath. We just have to worry about the fact that we want to add stuff to it or take it away. We're going to take a little bit closer look at how array lists actually work today as we get toward the end. Any questions so far? So that's pretty straightforward, I think. Yes, sir.
What is a key, like how you search for it?
Good question. The question was, what is a key? And yes, that's the answer you gave was also correct. A key is a way that you find some value. So when we're talking about the next data structure we have listed here is a map, right? Maps, which we also call dictionaries, also known as associative arrays, associate some key with some other value. A key is a way that we find something we're looking for, and the value is the thing that we want to find. So dictionaries are a really good example in this case because we want to find the definition of a word, and the way that we find that definition is we use the word. In the case of like a word dictionary, the key is the word itself, and the value is its definition. Yes, do you have a question? I answered it. Okay, yay, I answered your question before you asked it. So that's the idea of a map. And there's lots of ways we can use maps, but the whole idea is that we find some value by looking for some key. That is the fundamental purpose. It maps a key to a value. Yes?
Could they all be used for the same thing? So, for example, could you have a list of definitions, a set of key terms, and then the map is both of them together?
Right. So I'm going to rephrase what you said, but that's accurate. Yes. So you could have a set of keys, which are the ways that you want to access data, and then you can have a set of values. When you have key value pairs, that is when you have a sequence of key value pairs. That is when you have a mapping or a map. Does that answer your question?
And that relates to that's similar to the array elements. So, for example, array of element 5 is equal to this value.
Right. It's similar to arrays. So you could consider, strictly speaking, a traditional array as a very limited mapping from monotomically increasing integers from 0 to values. So an array is like a very, very limited form of an associative array. Yes, did you have a question?
Yeah, what's the difference between unique keys and regular keys?
Oh, good question. So I marked here for maps that we have unique keys, but we can have repeated values. What that means, because we're mapping from a key to a value in a map, that means we can only have one entry for a particular key. That's what makes it unique. If we have a key, it can only map to one other value. So we could have more than one key that maps to the same value, but every key can only go to one particular value. That's what it means. And likewise, we can have, that's what I mean when I say we can have repeated values. We could have more than one key pointing to the same value. That would be a repetition of that value. There's another variant that I'm not covering here, but I'll tell you about it in case you're interested. So you don't have to know this for a test or anything. It's called a multi-map. And a multi-map can actually map a key to multiple values. So it's like a map, but the keys are not unique. The keys can point to multiple values. But it is a more rarely used data structure. It's more complex, but it can be useful in certain situations. But most of the time, we want a key to map to a single value. So does that answer your question?
Mm-hmm. Yeah.
Yes, I think I saw a hand. Yes, go ahead. If it's a multi-map. Right, so a multi-map can map, the keys are not necessarily unique in a multi-map. You can have a particular key, and there might be multiple key value mappings from a single key.
How would you order that?
How would you order that? It's a mess. But basically what you would usually have is you'd have a key, and the key maps to a list of values. Rather than a single value, it maps to a sequence of values, and there could be a bunch of them. Does that make sense?
Why
Yes.
can't the list be ordered or a map be ordered?
So that's a good question. So the question was, why can't a map be ordered? And actually, some maps are ordered, but not all maps are ordered. This is one key difference between maps and lists, is that all lists are ordered. Every list has an ordering. You put things in a certain order, and that's the order of the list. Right? When you can sort them and change the ordering, but they have some inherent ordering. Maps, it depends on the type of map you implement. There's two main types of maps used in software. There are others that you could do, but the two big ones are, they're called tree maps and hash maps. Hash maps have a lot of randomization, and the ordering of a hash map is not meaningful. Because of that, we consider it an unordered map. The ordering doesn't have any rhyme or reason to it. It's more about maximizing efficiency than it is about holding the order that we put the elements in. A tree map, on the other hand, does have inherent ordering to it. So for maps, the implementation determines whether or not it's ordered or unordered. Does that answer your question? And we're getting like a broad overview here, but there's a lot more detail that you can get into if you're interested in these specific data structures. And you're going to learn all about them when you get to the data structures class, too. Yes?
Does the key need to be a specific data type, or can it be like?
Oh, that's a great question. The question was, does a key need to be a specific data type, or can it be anything? And the answer is, it can be anything that the language you're using makes a valid key. So in C++, literally anything can be a key. In Java, I believe it is limited to reference types. I don't think you can use primitives, if I remember correctly, as keys in Java. You can wrap a primitive in those box classes that we talked about, like the capital I integer class and stuff like that. But generally speaking, there's no theoretical limit on it. It's only any limits imposed by the language. Does that answer your question? Anyone else? Okay. So we've talked about lists, we've talked about maps. One data structure we haven't talked about, and that is not as common, but you still see it from time to time, is a set. So I don't think anyone here has taken, probably. Has anybody here taken COT 3100, the discrete structures class? Oh, you've taken it.
Yeah.
Okay. So a couple of you have. So sets are going to show up all the time when you take that course if you haven't taken it yet. It's a big, set theory is a big part of what we do in computer science. But a set is a group of unique values. And when we have a set, we are looking to see if we are checking, it's a way to track membership in a set, right? So we have a set of value, we have a set of keys. Those keys are all unique. A set has no values because it's not any kind of mapping or anything like that. The main purpose of a set is not to establish, so it's usually not used to establish ordering, although you can use it for that, as you can see right here. But its main purpose is to basically have a bunch of yes/no markers, like are you in a set or are you not in a set of things, some kind of classification. So you can add keys to a set, and you can check for keys, but if you try to add a key to a set that already has that key, in most cases, it'll succeed. It's not going to fail, but it's not going to add a new element to the set because it's already got that key in it. So if you have a situation where you only want to have one of a particular element inside of a group, and you don't want to have more than one, you just want to know whether it's there or not, that's a case where you could use a set. So for example, let's say that you had some kind of project you were doing, and you had a really long string that you had to parse, and there were only a limited number of possible characters, and you just wanted to get the unique characters in that set. You might use a set to figure that out, right? So that's an example of how you would actually use a set. And yes, if you want to, you can use that for that purpose, although it is due tomorrow, so hopefully you've written most of it by now. I don't recommend rewriting your project if you haven't even remotely close to that at this point. Anyone else? Any questions? Yes.
Do you sets and maps or lists many of those data types like inherit from one another?
Oh, that's a good question. The question was, do any of these types inherit from one another? These types usually do not inherit from one another. We are going to look at some abstract data types that do pretty shortly. These don't usually, but they do have similar underpinnings. List is kind of separated from these, but if you look at map and set, you'll see that both of them, like the most common implementations, are tree sets and hash sets. Just like for maps, it's tree maps and hash maps. And that's because they have the same underlying data structure. Key-driven data structures tend to be either hashed or they tend to be built from trees. When we talk about hashing, there's a construct you're going to learn about in a lot of detail in data structures called a hash table. And a hash table is used underneath both hash maps and hash sets to find keys because it's very efficient at that. Whoa, that was interesting. I'm sure that I did not do that.
If there's few enough people in the room.
Oh, is that what it is? There's not enough people in here?
It's either noise or sound activated, so we need to make one of them.
Okay, we need to be louder. That's the problem. Okay, so hopefully, does that make sense? Does that answer your question? So there's similarities under the hood, but at this point, we're not looking at derived data structures just yet. Anyone else? Okay, so in Java, a lot of abstract data types are either what we call abstract classes, which just means that they are they're not fully defined, or they're interfaces. We're going to talk a lot more about interfaces later on, but the idea is that you have a set of expected methods. So, for example, something we've seen a little bit of is that we played around a little bit with lists. So if we have a couple of strings, like if we have Santa's nice list and his naughty list, then we might decide that, for simplicity, we want to get an array. We want to take those arrays and we want to turn them into lists. And this is a way that you can do that. All the arrays class has an asList function, a method, and you can turn any array into a list. Once you've done that, you can use list operations, and I've just given one example here. You should take a chance when you have time to look at the Java list API. But once you have a list, you can manipulate it as a list. There's a whole bunch of provided functions that you can use. In this case, I'm just checking for containment. I say, nice list.contains Bob. That's just going to return a true false value. It's going to return true if a list contains that element. It's going to return false if the list does not contain that element. In this case, it does, the list does contain Bob, so the result is going to be true. Make sense so far? Right. So we're going to be looking at a lot of these abstract data types in the context of Java, but I want you to know that they're not strictly Java concepts. They exist in almost every single language, the idea of these abstract data types. And most modern languages have implementations and abstractions of these built right into the language. Okay, good so far? So, how many of you guys have ever heard of a queue before? Okay, a lot of you. A lot of you have heard of queues before. So queue is a type of container, something we also call a collection. And it's unique, what is most unique about a queue is that its ordering is first in, first out. The first thing you put in is the first thing that will come out of a queue. Did you have a question? Or no? Okay. So when we look at a queue, the behaviors that we expect from a queue are primarily that it will have an enqueuing behavior, a behavior that lets us add to the queue, and a dequeuing behavior, a behavior that lets us take things out of the queue. And when we dequeue things, when we take them out, they will be in the order that they were put in. So if the order we put things in is we put A in and then B in and then we put C, then the order they will come out when we dequeue is going to be A and then B and then C. So pretty straightforward? Yeah? Okay. So they're first in, first out. Some examples in languages, queues are often implemented using either a linked list or an array or array-backed data structure of some kind. So let's take a look at an example of what it would look like in code. Let's say we were building a jukebox. I apologize, you're gonna see a lot of terrible song names here. And we wanted to create a queue. In Java, because a queue is an completely abstract data type, we have to create some other type of data in order to hold a queue reference. In this case, the linked list type in Java gives us access to queue functions. So we can create a queue object, and we can use a linked list as its type. Does everyone understand that? I want to make sure I'm not losing anybody. All right. So we can create a linked list and we can say, okay, this linked list is going to be our queue. Yes? Okay, I lost you. Okay, so the idea here is that a queue, there's no actual queue class, right? It's abstract, so there's not an actual queue class. But other classes can say, hey, I can act like a queue, and linked list is one of the classes that does that. The linked list type that's built into the Java basic library, it has all of the queue functions, and it does what we call, you don't have to know the details of this yet, but it does what we call implement the interface of a queue, which is basically a promise. So the linked list class says, I promise to do everything that a queue needs to do. Does that make sense? Okay. Yes? So why don't I just call it a linked list? Well, that's a good question. And this is a short program, so practically speaking, if I was writing such a short program, I would. But sometimes I know that I need a queue, but I don't necessarily know what I need to back it right away. Or I might want to be able to have some options. Like, let's say I have a bunch of methods, right? And I need to pass a queue into a method. I might not really care about what type of queue that is. I might not care if it's backed by an array or if it's backed by a linked list. I might just care that it has the queue function, right? If I only accept the linked list, I'm limiting myself in how I can use that method. Does that make sense?
So why even use a linked list then?
Well, there's no basic queue type. That's the struggle, right?
Okay, so something has to be used.
Something in the case of a queue for Java, and every language is a little different. But Java has no built-in defined queue class. It has a queue interface, but not a class. An interface just means like you can promise to act like a queue.
Could you write code with a queue in it without saying that it's exactly what it is?
Yes, you could, but you couldn't create a new queue. Like that's the key, right? So I could take a queue in to a method and say, I'm going to use this as a queue, and then I don't have to care what type it is. But if I'm creating an object, I have to say what type of object I'm creating.
Okay.
Does that make sense?
Yes.
Yes.
Can you do queue int?
Gonna do, yeah, so, actually, int is a primitive, so I can't, right? So,
Can you
that's
use-
one, so let me talk about this a little bit more to give you some detail. So, the one big limitation in Java is that a lot of, especially container types or collection types, which is what all of these are, they cannot accept primitives. They can only accept reference types. So I could have a queue of integer types, like big I integer, which is the wrapper around integers. And I can have a string, and I can have any other type of class or any other type of reference type. But what I can't do is I can't have a primitive. So I can't have int or float or boolean.
What about string array?
So string is fine because it's a reference type, and array is fine because it's a reference type.
Int array?
You can do int array as well. Yeah.
Got it.
Get the idea?
Yep.
So as long as it's a reference type, I can do it, but I can't do a primitive type. Anyone else? Okay, so we're going to create this queue called songs. And then I'm going to add the song Barbie Girl to it. So down here, in case you haven't missed it, I am starting to actually, down in the, I should say this for the live stream people, down in the lower, from your perspective, left-hand corner, there is, we're going to be building our queue there. So I add Barbie Girl to the songs, and then I add Dancing Queen to the songs, and then I add I Need a Hero to the songs. So, and you'll notice that they're going in from front to back, right? When I take them out, let's say I want to go through, and as long as there's some stuff in the songs list, I'm going to pull them out and print them. As I pull them out, I'm going to pull them out in the same order that they went in. So the first song I'm going to pull out is Barbie Girl, and I'm going to print the name of that song. Then I pull out Dancing Queen, and finally I pull out I Need a Hero. In that order. Okay, yes, in the back.
What happens if we remove and then add? Would the thing that we most recently add be first in the queue now, or would it?
Right, so what happens if you remove something and you add it again?
Yeah.
So if when you remove it, you pull it away from the front. When you add it, it goes in the back.
What?
Does that make sense?
Oh, say that one more time. Can you remove it?
Okay, so he was asking, what if I pulled Barbie Girl out, but then I turned around and I added it to the queue right away again? then you'd pull it out of the front, but when you put it back in, it would go to the back. Because it's first in, first out. So basically, if you put something back in, it always goes in the back of the queue.
Oh, okay.
Even if it's already been in the queue before. Okay, any other questions? Yes?
What's with the songs.peak thing?
Oh, okay, this is a good question. So songs.peak. So this is an interesting method of the queue types in Java. Peak says, hey, I want to see if there's something here. That's what it says, right? If there is something there, it'll tell you what that something is. If it's not, it'll return null. What it doesn't do is it does not remove anything from the queue. It's peaking at the front. Does that make sense?
So that's where the songs remove thing comes in.
What's that?
That's where the songs remove thing comes in.
Right, that's where the songs remove comes in. Because songs remove takes something out and returns it. So in our case, it took Barbie Girl out and returned it first. Make sense? Yes?
Does it return the data type or the reference type, or does it return like the actual string?
It returns the reference to the string. So that's a good question. So what it does is there's a reference, like all this, and this is part of why Java only accepts references in these container types. It's always going to return a reference to the data, not the actual data itself. That is unique to Java. In many languages, it will return the actual value, so it's an important distinction to be made. But in Java, it's always that pointer. It's always that reference. Does that answer your question? Okay. Anyone else? Yes?
Can you return the reference without removing it in a queue?
Yes, you can get the reference of an element in a queue without returning it using peek. That's actually what I'm doing right there. That'll give you a reference to the first element, but it won't take it out of the queue. Does that answer your question? Anyone else? Okay, so that's queue. But it's not the only data type we're going to work with. We've heard this word stack before. And what we're going to see is that this is an abstract data type that's used all over the place. A stack is a type of data that is used in memory, it's used in compilers, it's used all over the place. And we have seen it when we are looking at the memory stack, when we're looking at what we call a call stack for a set of functions. And just like we build up slowly and then take from the top of that stack in the call stack, we're going to do the same thing when we're working with other types of data as well. So the key feature of a stack is that rather than first in, first out, it is last in, first out. By the way, you may have noticed I put these acronyms, LIFO and FIFO here. That's because people use those terms all the time. So you will see people use those, and it's really important that you understand that when people use that initialization, that's what it means. Because people out in the industry talk about it all the time. Like they'll say LIFO or FIFO, and they'll just expect you to know what it means. So be aware of that. So it's a last in, first out structure. So a stack has what we call a push behavior, which is how you push things onto the stack. And then it has a pop behavior which allows you to pop things off of the stack. So the add and remove, basically, when we talk about stacks, the terminology used is push and pop. Push to put things on the stack, pop to take them off. Make sense so far? Okay. So you'll hear these words a lot, and that's last in, first out. So very similar to a queue, linked lists and arrays are often used for stacks. So if we wanted to look at, now stacks are interesting in Java because unlike queues, a queue is completely abstract in Java. However, Java actually does have a stack class built right in. Another interesting thing is it totally uses an array. Right? That is how it's structured. So it actually derives from another class called vector, which is basically an array list. So let's say we create this stack for songs, and as you can see, I'm building it down here in the lower left-hand corner. And the first song we put in is Cemetery Gates by Pantera, in case you don't know. Then we're going to add the song Cowboys from Hell, and then we're going to add the song Crazy Train. So have you noticed something different about how these elements are being added?
They're getting added in reverse order.
Right, they're getting added in reverse order. Oh, it's telling me I've only got 10 minutes left.
Uh-oh. Whip out the credit card.
Stay with free. Okay. Don't worry, guys. I'll start another one another chat if I need to. So we put Cemetery Gates in. They're going to go basically we're going to be putting things in front of the other things, right? They are on top of the other elements in stack terminology. We're pushing them onto the front. Then if we turn around and we pop elements off, they're going to pop from front to back. So this is where the last in, first out comes. So if we pop the first element out, it's going to be Crazy Train, then Cowboys from Hell, and then Cemetery Gates. Right, so basically it's very similar to a queue, except it does it has the behaviors are kind of, opposites. Yes?
In the top left corner where it says queue, should that say stack?
It should say stack. Good catch. Yes. You can see my copy-paste errors at work. Sorry about that. Yeah, that should say, yes.
Where?
Who performed Cowboys from Hell?
Who performed Cowboys from Hell? That was also Pantera.
Wait, where's the mistake?
It should say stack instead of queue up in the
Top
corner.
left and the left box.
Yeah. Yeah, that was a mistake. It was just a copy-paste error. I use the same base for the slides. I will fix this before I post it. Now, much like queues, stacks are also usually built on the basis of some kind of list data type. In Java's case, the stack is built on the vector, which is like another variant of an array list. It's going to vary depending on the language, but a lot of times they're going to be built on list types. Okay, so the last of these linear types that I want to look at today, the last of the abstract data types, I have to stand up because my legs hurt, is what we call a deck. And a deck is a double-ended queue, and it basically acts like a stack and a queue. You can push or pull from either end, from the front or the back of a deck. So a way to visualize it is that it's like a deck of cards, right? And that's kind of where the clever naming comes from, because you can pull from the top or the bottom in a deck. So a deck is going to have a push and a pop behavior, but it's also going to have an enqueue and a dequeue behavior. So it's going to have all of those things. Common examples, probably not surprising. We have linked list decks and we have array decks, and those are the most common implementations. Now, these are not exclusive, right? When I'm listing these are just examples. They're not the only way you could implement these data structures, but they do tend to be the most common. So we have a lot of flexibility when we use a deck-based structure. So let's say, it should have said deck, I'm sorry. I'll fix that. So let's say that we had our deck data structure, songs, and we decided to add a few songs. First we add Smells Like Nirvana. So add is just our standard queue add, but then we're going to use the stack-based push. That means the next element's going to go in front, right? Because push always puts things on the front of a stack. And then if we do another add after that, it's going to go at the end, because the queue behavior is to add things at the end. Now, usually you wouldn't mix them up like this. I'm doing this to show you that it works, right? I don't recommend that you kind of mix and match like this, in general practice. If then I want to go through and I want to take elements out, let's say that I wanted to remove the last element, which is something you can do in a deck, and print it. It's going to print out, live it in the fridge. And then if I do a pop, which is our standard queue function, which pulls from the front, then it's going to print out Amish Paradise. And then if I do a remove, which is the standard queue function, it's going to also pull from the front, and that's going to print out Smells Like Nirvana. So the basic idea here is that a deck it has the flexibility of both a queue and a stack, but it also, something that it allows you to do that neither of those other abstract types have a functionality for, is it also allows you to remove from the end of the data structure. And this is pretty unique in regards to decks, right? So usually you only remove from the front, either with a queue or with a stack, right? But a deck allows us to pull from either end, not just one or the other.
What did you say pop was? Oh, sorry.
I'm sorry, what's that?
What was pop? Pop is just the middle
Pop
one?
is the way that a stack pulls elements off the front.
Okay, front.
Okay. Did you have a question? There's a built-in deck, yes. there is a built-in deck, and there's several built-in decks in Java actually, several input variants. So, anyone else? Yes.
What's the difference between pop and remove?
So the difference between pop and remove is that they are different names for the same thing. So in the case of a deck specifically, so they're just different terminology and they mean the same thing. Yes.
What's the V? The V. I've seen that.
Oh, the V is for value.
Okay.
So whenever I have key, K is shorthand for key and V is shorthand for value. And if you see like a capital T, that's shorthand for type. Right. So we've seen that before. But usually we use them to distinguish between key-based and value-based or key-value data structures. Does that make sense?
Yeah.
Yes.
I'm a little bit confused how the output ends up coming out. So what gets removed, what gets copied, what gets...
Okay. So do you understand how these elements should show up in the list in this order?
Yeah.
Okay. So the first call is remove last, right? So that's going to pull this last element off, which is living in the fridge, right? Does that make sense so far? Now, both pop and remove pull from the front. So the front of this list is Amish Paradise. And then if I'm pulling remove, there's only one element, but remove also pulls from the front, so then it's going to print smells like marijuana.
And since there's nothing else, if you were to try to do it again, then it would result in error?
Yes, in that case it would result in an error, yes. Yes, actually I think it would be, I'll double check. It would be either be an error or it would return null, one of the two. Yes, go ahead.
Why are pop and remove sort of valid? Like, why do they?
The reason that they're both valid is because any deck can act as both a queue and as a stack, and so it has to have both of those sets of functions. Because it's basically promising to act as both a queue and a stack, and so it has to provide all the functionality of both of those types of data structures. That's really the only reason, though, is because it's fulfilling a promise to serve both of those needs. Does that answer your question? Okay. Yes.
Why have a queue or stack when you just have a deck?
Why have a queue or a stack when you could just have a deck? That's a good question. And the answer is usually, so the answer is a lot like the answer for why would we bother with encapsulation and making things private. And that is that sometimes we know, most of the time, a stack or a queue is what we actually want. Most of the time we want one ordering or the other. So it's kind of defensive programming to use the data structure that best fits your actual need. If you use a deck, you're basically opening yourself up to making mistakes, right, which you would like to avoid most of the time. There's also optimizations you can do if you only need to pull from, if you only need to do first in, first out, or last in, first out. There's optimizations that can be done in the data structure itself that you can't do if you have to have the ability to pull from both ends. Does that answer your question? And then, yes?
How do you call on the deck if you don't want to remove it? How would I print it?
Oh, how would I print? How would you print it without having to remove it? Well, you can. The peek operation exists just like it does for stack and queue. So you can look at the first element. I think there might be one to look at the last element too. I'd have to check the API. Strictly speaking, for decks, you're only supposed to. So a deck abstract data structure only promises to let you get the front and the back. It doesn't make any promise about being able to get stuff in the middle. So, and that's true of stacks and queues as well. Strictly speaking, those data types are built to limit access to one end or the other. So, you can look in Java and in many other languages at the first or the last element in a deck, but you usually can't get to the stuff in the middle. Does that answer your question? And the reason, again, goes back to the answer to the previous question. We want to protect ourselves from making mistakes, so whenever we can, we want to, limit access unless we really are sure that we need it. Yes?
There's a peak last function.
Oh, there's a peak last function. Okay, so that answers the other half of it. So, and I'm pretty sure that it's gonna that my system here is gonna kick us out of our meeting soon. But let's keep going until we run out of time. We have 5 more minutes. So those are the apps. Oh, yep. This free meeting has ended. Hold on, I'll post another one to everybody. for using free stuff and being poor. Okay. Okay, so we can pick up right where we left off. So, those are the main abstract data types I want to cover with you. Moving beyond that, one of the interesting data structures in Java that we've looked at a little bit, we've played around with, and a lot of you have seen, is the array list data structure. An array list, which is also called a vector, often in computer science terms, which is different, completely different from the idea of, well, mostly different from the idea of a vector in math, right? I mean, they're distinct concepts at this point. But the idea is that you have a list that is backed by an array. You have a list that underneath is an array. So, in this example here, I'm actually building off of one of our previous examples. So we have a song, and I create an array list, and this here is the array that lies underneath this array list. So the array list has some kind of array built into it. So it's going to have some size, some initial size. In our case, that initial size is going to be 4 in this example. So we create a new array list, and then we start adding songs to it. And the songs are repeated in this case. So we're going to add some songs to it. First, we add Cemetery Gates. Now, one thing you're going to notice is that it's going to start adding from the front back. So keep that in mind as we go. Then we're going to add Cowboys from Hell, and then we're going to add Crazy Train. So you may notice we haven't actually used the whole array, right? So that means we're allocating more elements for the array than we actually need. Why do you think we're doing it? Why not just start with like a size of 1?
How did you set the size of the array?
Oh, good question. How did I set the size of the array? The answer is I did not set the size of the array. The array list set the size of the array, and I didn't have to worry about it. But why do you think it doesn't start at like the smallest possible value? What do you think in the back? Yeah, well, so that's one thing. If it has to move things around, it has a little blank space. What other reasons can you think of? Yes, what do you think?
It's going to have to, the underlying array is a fixed size. It's going to have to be recreated if it exceeds the number of elements.
Yes, so that's the right answer, and so I'm going to repeat what you said. So arrays, they have a fixed size. Once you declare an array, that's the size of the array forever. If we have more elements than we have space in the array to fit them, what do you think we have to do?
Make a new array?
We got to make a new array. We got to copy everything over, and then we got to delete the old one. That's a lot. That's an intensive computation. When you talk about like computing time that it takes to execute operation, that's pretty expensive. Yes, did you have a question?
Oh yeah, for that one type that you put in like this way and it comes out this way, what if you put in one element and then you ask it to take out, does it take out empty until it hits that one element in the front?
Oh, so you're saying like, will it take out empties in this case?
Yeah.
And give it back? The answer is no, because what happens is the array list also keeps track of how far it's filled.
Oh, true.
So it'll return the last thing it filled in that case. Make sense?
Yeah.
Okay. So, then let's say that we decided we were going to remove elements from the back. In this case, this is a little bit complicated, but what I'm saying is I'm going to pull the element at index size -1. So the size, in this case, is 3, right? Because we have 3 elements in the array list. Size -1 is 2. That's going to, the reason I subtract 1 is because everything starts at 0. So 0, 1, 2, that'll be the last element. So we grab the last element, which is Crazy Train, and then we grab the next to last element, which is Cowboys from Hell, and then we grab the last element, which is Cemetery Gates. Right? Okay. Does anybody have any questions about this concept?
If you grab the empty, it spits out null?
Yes, so if you try to grab something, well, first of all, I'm checking is empty, right? Is empty returns true or false. If I've already taken everything out, then it's going to return true. If there's still stuff in the array list, then it's going to return false. But if I try to take out an element when one doesn't exist, it depends on the implementation of the data structure. Some of them will return a null. Some of them will throw an exception. But it depends on the data structure itself.
Yeah.
Yes, in the back.
So the song size like changes as you take out elements, but is there like a code that has like the length of all four?
Of the underlying array?
Yeah.
In array lists, I have to double check with Java, but in most languages, yes. You can access, we call it the capacity of the array list.
Okay.
So it's not the same as the size. The size is how many elements you have in it. The capacity is how big the underlying array currently is.
Okay.
Yes?
So we start with the array, we add 3 elements. So it'll add one additional empty element space if you want to put something in or change it.
Well, it's going to allocate a set size. In this case, I said 4, but the truth is it depends on the language and even the version of the virtual machine. Like Java has new versions of the virtual machine all the time. But it's going to come up with some initial size, like some default size for the array. And it's going to start until it runs out of spaces, and then it's going to have to create a new array, right? So usually that size is picked so as to minimize the likelihood of recreating a new array, but it varies a lot depending on the underlying implementation. Yes?
Do you know how much Java changes the size? I know in one language I worked
I honestly
with
don't.
like double it.
I would have to look it up. They may not change it very often at all. Well, you're talking about when it runs out of space, right? Yeah. So when it runs out of space, the common behavior in most languages is, as the gentleman here said, either to increase your capacity by 50% or to double the capacity. So yeah, sorry, I guess I misunderstood what you were asking. But yeah, different languages have different ways of implementing that. But usually it's either add 50% or double, one of the two. Okay, so one other thing you might have noticed, I just want to point this out before I let you go, is that this is kind of, the way we're doing this is kind of acting like a stack, right? We put elements in and we're bringing them out in the same order. That is not an accident that I did it this way. And in fact, many times we're going to implement a stack using an array-based data structure because pulling elements off of the back of an array-based data structure is cheap. What do you think happens if we try to pull an element off of the front of an array-based data structure then? Yeah, we basically have to shift everything over. So we basically have to copy everything into the space before it if we take something off of the front of an array-based data structure, which is really inefficient. So stacks are really good match with arrays. Queues are not so good because we're usually putting things in one end and pulling them out the other. All right, we're out of time, and so thank you for coming. If you have any questions, I'll stick around. Take care.